Now, and our target in SARS-CoV-2 is the protease enzyme. You know, I told you there are different targets that you can target on SARS-CoV-2. You can target the spike protein. You can target the protease enzyme. You can target the RDRP, RNA-dependent RNA polymerase enzyme, and other targets like that, right? But for this study, we are targeting protease enzymes. So we downloaded some drugs from PubChem. We downloaded aspirin, ibuprofen, right? And we also designed two structure on our own, right? And I said, when you are, so those are the 4 drugs we want to test against this enzyme, whether it's going to, they can inhibit this enzyme or not. And I also said to you that when you are designing drugs like that, you must have a reference drug. And a reference drug is a drug that has been known for the target that you are designing, that you are focusing on. It must be a known drug that is being used medically for the target that you are working on. And I suggested we use lopinavir. Lopinavir is an antiretroviral drug used against HIV protease enzyme. And it has also been used for SARS-CoV-2 protease enzyme, right? So that's why we are going to use that as our reference drug. So that is done. So now we have, and I taught you that I've shown you how to download your compound. And last meeting, we look at where you can get your protein structure. And this is the protein structure that we got for SARS-CoV-2 protease enzyme. And I said to you, another thing you must understand on your protein is where is the catalytic site or the active site of your protein. And I made it clear to you that even though you have a padlock, a padlock, right? It is not anywhere on the padlock that you can put your key to unlock that padlock. No. There is a point on that padlock, on that lock, where you put your key. That point is the catalytic or active site of that lock. The same thing is applicable to biological targets, enzymes, like the protease enzyme. It is not anywhere on this structure that you can dock your drug on for you to be able to stop this enzyme. It has to be on the active site. And I remember I said in our last meeting that there are different ways you can know the active site of a protein. Number one, you can read about that protein by putting a simple search on Google link, right? Like we did last time. What are the catalytic or active site amino acid residues of SARS-CoV-2 protease enzymes? And it made us to understand that if you can find 16-145, anywhere 16-145 is, around that place is where the active site of that enzyme is. So please give me 1 second, please. Okay, so I said you can search for the catalytic site of whatever target you are looking online. And we did that, and it made us to understand that if we can find the 16, if you remember CYX 16 for at position 145, 145, that is where the active site of that enzyme is going to be. And I told you guys that how do you do that? You can go to tools, general controls, command line, right? And it will give you this command, select SEL column space 145, and it will definitely highlight it for you. This is what it is. So what that means is the active site of this enzyme is around this place. That was one method I said. The other method I also mentioned, you guys, is you can, if you download from PDB, there is tendency, there is probability that you are going to download a structure that has a drug attached to it, right? You can read about that paper, and most of the time, where that drug binds to on the enzyme is usually the active site of that enzyme. And I give you an example. When we downloaded this structure from 3B, it shows to us that it was attached to a drug, right? And I told you that how do you get that? You can come to select residues, and we look at, that the name of that drug that was attached to was GWX. Can you see? This is where GWX is. This is where our 145 is. So that means it is true that this drug is binding at the active site of this protein. So the docking we want to do, and I said to you last time that molecular docking is you putting your drug, your compound, your compound at the active site of an enzyme. If you want to open a door, right, and you have bunch of keys in your hand, for you may not be able to know which one is the right key for this door, right? Am I correct? And the best way you can do is you will keep taking those keys one by one and begin to insert them at the point of the door and say, okay, which one is going to go in, which one will open. That's how you do it one by one. So in the same way in drug design, when you have a lot of compounds, the best way you can know which one is going to work against that enzyme is to put those drugs at the active site of the enzyme. And that's what is called molecular docking. So we are going to do molecular docking today, and we keep putting each of those enzymes at the active site, each of those drugs, compound, at the active site of the enzyme. Now, how do we know which one is going to work? There are two ways we are going to know which one is going to work. The first way is when you put it at the active site of this enzyme, this software, Chimera, will give us a score, called docking score. That docking score is a measure of how comfortable the drug that you put there is at the active site, right? So it will give us a kind of energy, a docking energy, and it's usually in a negative value. So the higher the negative score, docking score, the better the drug will be at the active site. So let me set this key to. Okay, guys. Yeah. So what I was saying, so we are going to do molecular docking now, and we are going to put each compound. I'm going to do one for you, right? I will show you how to do one. Then I will send you guys the other compound, and you will do that and give me the docking score. So let's say we have two drugs now. Drug A is giving us minus 10 kilocal per mole. That is the unit of the docking score, minus 10. And we dock another one, and the other one is giving us minus 5 kilocal per mole. What the docking score for the two of them is saying is the one that has minus 10 kilocal per mole has more probability of inhibiting that enzyme than the one that has minus 5. Are you guys following me? That's all. Now, let's now go to molecular docking. And I want you guys to please listen and follow this instruction very well. Listen and follow the instruction very, very well. Listen and follow the instruction very, very well. Now, how do we go about this? The first thing I want us to start from what is called, I want us to start from ligand preparation. So the first thing we are going to do is ligand preparation, right? And I said it to you, when I'm talking about ligand, I'm referring to your compound. So let me take off this, close. So let's go back now. Open. So let's use aspirin. It's a ligand that we want to use today. Aspirin. Please, I want you to take note. I will upload these videos for you to watch, but I want you to guys to listen carefully. Now, this is the structure of aspirin. So the first, there are three parts to molecular docking, or let me say 4 parts. Number 1, take note of this: ligand or drug preparation. Ligand/drug preparation. Number 2, your target or protein or receptor preparation. So you prepare your drug that you have downloaded the structure, you prepare the protein that you downloaded the structure from PDB. After that, we set what is called grid box. You set what? Grid box. Then the last one is the docking. The docking. So the first step is what you are going to do now, and that is called ligand preparation. Right. Now, under ligand preparation, can you guys see my screen?
Yes.
Okay. So under the ligand preparation, right? What we do here is we do what is called structure minimization. We minimize this structure. What that means is, in when you are doing compound structure, there is what is called a valency. For instance, carbon must have like either 4 or 6 valency compound structure attached to it. So we have to make sure that every element, this red is oxygen, this white is hydrogen, all this gray, or what can I call it? That's carbon. They must have the required number. Yeah, it's carbon. They must have the required number of hydrogen or bonds that is attached to them. So this is, you can see this UNK 1.A O1. That's oxygen number 1. If you put it here, it's going to be oxygen. Then you see oxygen 3, number 3, oxygen number 2. You put on the white, that is hydrogen number 8. So make sure that everything is having the required number of hydrogen, oxygen, everything. We must do what is called minimization. And in this minimization too, we must do what is called, we must add charges. We must add charge. So that is what we do. So how do we do that? Go to tools. Click on tools, right? Scroll down to structure editing. Structure editing. I can do add hydrogen, add charges separately, but that may take me longer time. Just come down to minimize structure. That's what I call structure minimization. Click on it. It will give you this box. Everything on this box, leave it, don't touch it. Click on minimize. Once you click on minimize, let me try to bring this down. And this thing. When you click on minimize, okay, great. Oh, no. When you click on minimize, right, it will give you this. Yeah, it will give you this box. It will give you see this number is just the PDB code of aspirin 2244. So a PubChem code of aspirin. So once you have this, make sure everything is the way it is, then click. So it's going to then add hydrogens to this compound. This is the PubChem code for aspirin. Add hydrogen to it. Click OK. It will add. So we have added hydrogen. The next thing is add charges to it. So there are different force field, standard force field on Chimera. The latest one that we have now is the amber force field 14. It will be on 14. Then let this other be on that is jar, right? Once that is done, click OK. Look at the structure. Then it will give you this. It will give you this information. On this thing. You see, it's giving us our compound. The net charge on this compound is +0. So it added charges to it and make sure the charge is 0. Just leave everything. Then, so I will click OK. I want you to look at what is going to happen to the structure of the aspirin on the screen now. Okay. Can you see what happened to it? It stretched out. It does what? It stretched out. If that doesn't stretch out, there's going to be a kind of static force, internal force that will be affecting one atom to the another atom. So you must make sure you do this for your ligand so that it can stretch it out for you. I can make it to have the orientation. How do I explain that for you? It's like when things is being close, imagine you are in the class and everybody is too close to each other, right? You are too close, so you hardly have time to stretch your leg, stretch your arms, or stand up. So if that is exactly what happened to the compound before we did minimization, right? And if you do docking with that, it's not going to work because the enzyme, each of the structure on the drug on aspirin won't be able to function well. So when we add charges and we minimize, it was able to stretch. They were able to create more space for themselves. That is what happened. So once that is done, what we just did now is ligand or drug preparation. We have prepared our drug. So what you do now is to save it. Let me click Control 5. Don't forget you save drug as what? Mode 2. Save mode. So I'm still going to save it in that. Let me name it prepared just prepped underscore aspirin. That is the one I'm going to want to use for docking because it has been minimized. So once you do that, just save your structure. I'm still saving on iArt. Save. We have saved this. So this is the prepared one that we'll be using. So close session. So the first stage has been done. We have prepared our ligand, our drug. Any question on this so far? Any question? Okay, thank you. So the next thing we do now is we move to protein or receptor preparation. When I'm using the word biological targets, protein or receptor, I mean they are the same. So let's now go to our protein structure that we downloaded from PDB. So let's go back, file, open. Do you guys have this box open for you when you open it? When you open the structure on Chimera? It's not so, I don't know why my own is it's supposed to open for me directly. I don't be choosing whether it's PDB or not. Now, we want to prepare our drug, so our target, our protein or receptor or enzyme for molecular docking. And don't forget, I advise you to always use mouse for this. Now, when you want to prepare drug for molecular docking, your protein, what do? Don't forget, for ligand, we add charges and hydrogen. That's what we did under minimization. In this place, for protein, there are quite a number of things we will do. Now, for this protein that we are working on, if you know that the normal standard component of every protein is amino acid. So anything that is not part of this protein will be deleted. Anything that is not part of the protein will be what? Be deleted, right? So for this protein, only the amino acids are what are required. No other things are required. No other things. So anything that is not the amino acid on this protein will be what? Will be deleted. So let's go to residues. How do we see what is there? Select residues. Now, can you see? We have non-standard and standard residues. Standard residues are the amino acid. They are the normal part of a protein. Now, non-standard residues are this structure, DMS, DWX, HOH. That's water. Right. Now, let me say this. For some proteins, for some enzymes, we call them metalloenzymes. Metalloenzyme, yes, they require additional, apart from amino acid, they require something else to perform their functions. For instance, hemoglobin that carries oxygen in our blood, apart from the normal amino acid, it requires what is called a fulfilling ring structure. I won't go fast to that, please. Just let me stay. So there are some enzymes that, apart from their normal amino acid, they also require some other metals like zinc, magnesium, cobalt, nickel, right, for their activity. So if you have that kind of enzymes, you are not going to delete those metals because they are part of the enzyme. But for this one that we are working on, there is no metal is required. So only the amino acid. So let's start deleting. Let's first of all delete DMS. Click on DMS. I like DMS. It's not part of this. So the next thing to do is to what? Delete. How do you delete? Go to action. Go to atom/bond. Then you will see delete down. Delete. We delete that now. Let's go back to residues. Which other non-standard residues is there? DWX. That's the drug that those people that did the experiment binded to it. So we know this is the active site now. Let's delete that drug. Go back to action, atom, delete. So which other one? Let's go back. Do we still have any non-standard residues? Water. So we can see some water molecule. Go back to action, atom, delete. Do we still have any other non-standard residues there? No. We have deleted all non-standard. So what we have here is standard residues. Great. Our protein is ready. So don't forget, we know this is where the active site is. So now, in this point, for protein, we are going to remove oxygen, because by the time we are doing the software is doing docking for us, is going to add its own hydrogen. So it is required that we remove our own hydrogen now. Let's go to select again. Go to chemistry, element, hydrogen. So it selects all the hydrogen on this structure. So what we need to do, let's go to action and delete all of them. Delete. So we delete every hydrogen on this structure. If you go, there are times that if you go to select and if you click element, hydrogen, it's not selecting anything. That means hydrogen is not on it already. So if you click delete, it's going to delete the whole structure. You have to start again. So once you choose and it's not showing you any highlight, it means hydrogen is not there. So you see now it's not showing me any highlight because we already delete the hydrogen. So once we have done that, I'm telling you, we have prepared our ligand, our protein. So let me give you so for ligand or drug, you minimize. And what minimize means is add hydrogen, add charges. For protein, all the enzymes that you are working on, you delete non-standard residues, right? And you delete hydrogen. Once that is done, then let's save this now. Save, don't forget you save your protein as PDB, not mol2. Save, so let me call it prep protein. Prepared protein. So let's save now. Save. Now, we have done the first two stages. We have prepared the ligand. We have prepared the protein. So now, the next thing now is to now go into our actual docking now. Into actual docking. So once you have to, let me close this. Close session. So now, for you to be able to do your docking, you have to open your protein and your ligand together. So let's look for prepared protein. Let's open it. Let's maybe look for PDB. Okay. So this is our prepared ligand, right? Now, let's look for where amino acid residues 145 is. Can you see it here? So this is where we are going to, this is the active site we are going to create now. Once you open your ligand, let's go and your enzyme, let's go and open the compound too. I want to see the compound here that we want to dock. That's we have prepared aspirin, right? So you open the two of them. So you open the ligand first, sorry, the enzyme first, then the ligand next. Yes. So we have, this is the drug, this is the protein. What do we do now? The way it is now, we should do docking, right? Our enzyme may not bind at the active site. It could bind anywhere on this. So what we need to do is to create a grid box. And what is a grid box? A grid box is like a box that we create, telling our software that please, when you are docking, only dock the ligand anywhere we create grid box. If we should do that now, our drug may bind here, might bind here, might bind anywhere. That is not what we want. Am I correct? Are you following me? What we want is for our drug to be able to bind at the active site. And how do the drug know the active site? By, if we create a grid box, we create a box around the active site. So when you do the docking, the software is not going to dock your drug outside the grid box. It will dock it inside the grid box that you have made. And how do we create grid box? I want you to take attention. This is one of the technical part of docking. Go to tools, scroll down to surface binding analysis, then go to Autodoc Vina, and it's going to give you this box. It's going to give you this box. So this is the box where we are going to set parameters for docking. That's the box where we are going to set parameters for docking. Yeah. Now, so the first thing you do here, you must feed this box. The first thing is asking you to form what is called output file. Click box. So in this place, you let it know that you want your docking to be in this folder. So give it a name. We are going to give it a name. So let's call it prep. Let's call it protease underscore aspirin, because we want to dock protease with aspirin, right? So let's just say set output location. Just give it name. It's set. Now, number 2 is asking us. We have two structures on this box, on the workspace, the drug and the enzyme. Which one is the receptor? It's asking us. Protein, underscore protein is our receptor. Is underscore protein our ligand? No. We have to click on it. This is the PDB code for it. This is the PubChem code for our aspirin. You can change this name to you can change it to aspirin yourself. Now, so we have we have made it known to the computer that PEP underscore protein is our receptor, and this one aspirin 2244, that's the PDB code. I should have changed that name into aspirin. It's our ligand. Great. So the next thing now is to set our grid box. Is to set what? Grid box. Don't forget, this is where 16145 is. So we are going to set our grid box here. Here, right? So how do you set grid box? The first thing you need to do is just make your grid box to appear first. So just put 12 into this, box, into this box dimension. 12, just give, I can put, I just put 12, you can put any number that you like, and click on this. The box will appear. That is the grid box. Is this where we want our box to be? Everybody? Is that the active site?
No.
No. So it is now left for us to move that box to the active site and make it cover the active site. And how do you do that? If I should click on this now, see, I can't move the box. I just put down and try to, I'm moving it. It's not moving. It's moving the box and every other thing. That is not what I want. What I want is just the box. How do I move the box only? Let's go back to this. So you can check this, resize search volume using, check it. button 2, let's see if button 2 is going to move it. Still not moving it, right? So that means we need to go and choose a different button. Let's choose button 1. Button 1. Now, can you see? Can you see? So you can use this to increase the size or reduce the size. And if you, but this is not where we want our box to be. So you can come to the edge like this and click on the edge and bring it down. Right? Just put it on any of the edge. Because on any of the edge, then press down your this thing, right? Then you can move it around. So let me, like I put it here, I can see where I'm moving it, but I want it to be here because this is where my active site is. So now it is there now. I want us to cover this area. So your grid box must cover all the structure of the enzyme on this area. So let's increase the size a bit, right? Let's try to increase the size. You know, this may be difficult for the first time, but with time we are going to get it. So once it's there now, but I'm just this what I just did now, I move it, but I can't be sure whether I've covered the whole thing. What I can do is to move the whole structure. And for me to move the whole structure, I need to go back to this box again and let me uncheck it. And let me now move, let's turn it and see. Can you see? Did you cover the whole active site? Eh? Guys?
Yes.
No, we
Yes.
didn't. What about this side? Our box is here. We didn't.
Oh,
So you have to keep moving the structure. So let me go back. I want to move the box only now. Let me go back and check it now and move it now. I have to make sure that you will keep moving it until you're able to cover the whole structure. So I'm moving. This is one of the tricky part of this thing. It is the tricky part, and that is the last stage of docking. So that's fine. Let me see if I covered everything. Let me go and I need to move the whole thing. So you have to be going front and back by checking. Can you see? I've not covered a lot. So let me go back again and check the resize. Let me move it down. So if you click outside the box will disappear. That's why you have, if you are using laptop pad, it will be stressful. But if you use mouse will make it more easier for you to work with. So let's go back and see if I cover the active side very well. Let me go and move. I need to do that. I need to uncheck this so I can move the old structure. Can you see? Can you see? You see, I think I have more. There are more space here. So I need to move it to this side very well. So let me go back and move the box again. So that's how you keep doing it until you get the perfect positioning. I don't want that side to be too. So let's go back and check it if we have covered the whole active side. You see, as you are moving the box, can you see that the coordinate for the centers and the sides are changing? So let me move it now. Oh, I think we covered majority of it. Yeah, I think we covered, but I think let's move it up again. Let's move it up more. Let's move it up more. So this is the most tricky part of the whole thing. But I'm telling you, if it's difficult for me because I'm teaching you. If I'm the one doing it, I will have finished this in like maybe in 1 minute. So what I'm saying is, by the time you guys keep doing it, you become an expert in it, right? And you get it. You become an expert in it and you get it. So Yeah, so I think we have a very nice. So can you see that everything about the active site is already in my box? Can you see the box from the top? Everything about the active site is already what? In the box. So what we just did now is we have made it known to the computer that anytime you are doing your docking, do not dock anywhere but only in this box. That is where we want you to dock, only in this box. Now, let me now show you another thing. Now, if you look at these figures, can you see we started with 12, 12, 12? Haven't it changed? It changed, right? So next time, if I want to do the docking, right, it's better take note of these values. You can screenshot it, right? So if I want to, I'm dealing with aspirin. I want to go and do another compound. Instead of me stressing myself, finding the grid box, just put these values directly in the center. It will automatically create my grid box where it is right now. Do you guys get my point? It will automatically create it at that point. Let me screenshot this so that if you need it next time, I won't have to be. Okay. So I purposely, so that next time if we want to work with this, we won't have to be doing that stress that we just did now. So the grid box is what is set. So when you do docking, your dock is not going to dock anywhere. It will only dock in the grid box, right? So so don't forget, we have set the output. We have identified the system, which one is the ligand, is the enzyme, which one is the ligand. We have set the grid box, right? At this point, just leave this one the way it is, true, 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 false, right? The next one, ligand option. Let it be the way it is. Advanced option. Now, what this advanced option is, this first one is, when we do the docking, right? This software is going to tell us the best way that this drug can be at the, can get position than this drug can be at the active site, right? You may know, if you like, you may do 10. If you like, you may just say, give me the best 5 or the best 4. Let's say you should give us the best 5. The best 5 position for this drug to be able to fit in at the active site of this enzyme. Any other one, let's leave it this way, right? Now, this is the last stage, right? So this is what is called, we have local. I know this, initially you can do Chimera with internet, but they have advanced. This thing I'm doing now, this Chimera, this molecular docking, you can do it even on plane. Anywhere, even if there is no internet, you can do it. And for you to be able to do it, you need a folder called Vina folder. Vina folder. That Vina folder is not here. So I have to go and get that Vina folder and copy it here. So I'm going to let me search for a Vina folder. Okay, I have one here. Where is the Vina? Okay, so let me copy it. So that Vina folder, you must always have it anywhere you are doing your docking. So let me go and copy it in iArt. So don't worry, I'm going to send you guys link this Vina folder, right? So this Vina folder has script for molecular docking to be done locally without you being connected to the internet, right? So that's what is in the Vina folder. So let's now go back. So on this place now, I keep local. Local means just do it on my system. Don't use internet. And if that is the case, I have to go to browse, go to iHeart, right? Click on the Vina and click on vina.execute. That is the executable file, right? That we need, right? Executable file, then click open. That is done. So Now we have done everything. All we just need to do now is to click OK, and molecular docking will be done. So before we click OK, which process is not clear to you? I can run through it. Questions?
I have a question.
Okay.
How do we get the Vina file with the execute?
I'm going to share the link to you. I'm going to send it to you guys to have it.
Okay.
Yeah. No, I'm going to send it to you. Any other questions? Anything that is not clear up to this point? If you can probably drop it, you can drop a chat if you're feeling shy. I want to be, since nobody's asking me any question, I want to believe it. Everything is clear, right? Okay, let's continue. So we have set everything. We have set the output. We have identified which one is the protein, the receptor, which one is the ligand, the drug. We have set the grid box. We have identified the Vena file. Just so when I click OK, you will see, can you see what is happening here? It's going to start running. Can you see? Running. So it's doing the docking by itself now. You just wait, it will give you the results. Running. It's running now. Look at this, running. By the time it's done, we are going to see the result. Still running. Still running. So let's wait. Great, it's done. Our result is out. Our result is out. Our result is out. Can you see? It puts the drug at the, can you see the drug, the one in green, at the active site? Now, if you look at this, the first one, what is the docking score for the first one? Anybody? Minus 4.8. Are you with me? Hello?
Yes.
Yes.
Minus 4.8. So this first one is the best position that aspirin can attain at the active site of SARS-CoV-2 protease. Now I'm going to change it to the next one, the one that has minus 4.5. When I click on that, I want you to look at this, how this is going to change. Click on now, look at it. Can you see the orientation changes here? Hello?
Yeah.
So you're saying that if this aspirin is standing like this, the docking score is going to reduce to minus 4.5. Don't forget when we are setting it up, we ask him to give us the 5 best position. So let's look at the third position. Can you see? Minus 4.4. Look at the orientation here. Let's look at the fourth one, minus 4.4 again. See the orientation here. Look at this. See the orientation here. So the best one is what? Minus 4.8. Minus 4.8. So when you do your docking, I want you to take note of this. So you take note aspirin, docking score for aspirin for protease enzyme that we just did is what? Minus 4.8. Minus 4.8. So you take note of that. Now, so once you know, so we are going with the first one, right? The one that has the highest docking score. And what is the model number? Is number 3.1, right? So let's go back, and so we need to save this complex. That means the enzyme with the best position, the 3.1. So let's go to, so in this case, we are saving protein and the ligand. So it's going to be in PDB. Save PDB. So let's give it a final name. So we are going to call it final complex because it's a complex. Now we have the drug and the protein want to save together. We have been saving them separately in the past. We want to save it. So final complex for protease and aspirin. It's good to always save it correctly, like we know. So when you want to save it, you have to click on the protein. don't forget the protein, right? Then you click on control. So we are saving the protein. What is the number for the best dog? 3.1, right? Are you guys following me?
Yes.
Yeah.
So let me show you. This is the protein. This is the ligand that we use to dock. This is the dock ligand. The best position is 3.1. The next one is the best one is 3.1 that has minus 4.8. The second one that has minus 4.5 is 3.2, right? Up to the 51. But the only one that we want is this, the best one. The best one is 3.1. So you click on the protein structure and you click control and you choose the best dock position that you want. Those are the two that you will choose. Now, so come here, uncheck all this, check. You now say save relative model to your protein, the prep.protein.pdb. Save multiple model in a single file, right? So once that is done, click on save. So if you go back here, I think it's save most of them in. So it save it. So this is the final complex that we did. We save it in iArt in Vina. So it's not supposed to be. We forgot to change that. So close this now. Once you close this, you can close this too, right? So let's take that from. It shouldn't be in the Vina. You're supposed to save it in. It should be on the iArt here. Right. That is it. So let's open it. Open. Let's open. So we save it. Final complex, right? iArt. Where is this? Is it? It's not supposed to be giving me this every time, but I'm sure yours shouldn't give you PDB. Can you see? Can you guys see this now?
Yeah.
Yes.
That means our drug is now docked at the active site of the enzyme with a docking score of what? The docking score of minus 4.8. Docking score of minus 4.8. Docking score of minus 4.8. The docking score of minus 4.8, right? So that is it. So now, the question now is, how do we know if aspirin is going to be a good inhibitor of this enzyme? So, and that is the assignment I want to give to you guys. Now, you repeat this process for lopinava, right? And the drug that you design in our first class, I taught you how to design. So you are going to do, at least design 2 drugs yourself and use lopinava as reference drug. So the assignment you are going to give me on Monday will be what is the docking score for lopinava, aspirin. I already did aspirin for you, so taking of docking score of aspirin is minus 4.8. So what will now be lopinava and the 2 drug that you design yourself, 2 structure that you design yourself. So get me the docking score of the 4 of the 3 of them together with aspirin. So when you do that, by the docking score, you yourself will know which one has something close to lopinava or more than lopinava. Anyone that is close to lopinava or more than lopinava in docking score will be the one that will likely inhibit this enzyme. Is it clear?
Yes. Yes.
Any question for me, please? The one thing I like to teach students for them to understand, and they should be able to do this independently. Ask me question now, and I will go back and do whatever demonstration I need to do. Any question? I'm going to upload this video now. I think of you do you still remember the YouTube channel?
Yes.
Okay. So I think I did our last meeting on Friday. I uploaded it already, so I'm going to upload this one. So you can, if you want to, if you have any question, let me know. And I'm going to send you a link now on how you can download, how you can get the VINA file. I will send you that link. I will send you a link now. Any question?
No.
Okay. Is it
I have
clear?
a question. I have a
Okay.
question from before.
Okay.
How we had our ligand and it was 2244. And that's aspirin. You said we could change it to aspirin.
Yeah, we can change it. Let me show you how to change it.
Yeah.
So by the time you open, let's open the previous one we use aspirin. So instead of having it to have the aspirin, why is this thing? I think I will go and download another Chimera. I don't know why. So by the time you are doing minimization, you are preparing the ligand, right? I think I should be able to. Oh, I thought I should be able to. Oh, let me see. Oh, it's not allowing me to change it. You can't change it, just leave it, right?
Okay.
I thought I will be. You can, yeah, just leave. Since that's the only ligand, you know that code is just for the protein you're working for the compound that you're working on, right?
Yeah.
Any other question? Any other question? I want to believe it's clear. So please let me drop what I'm expecting from you in the chat. So docking score for lopinava and two. Okay, let me see. Lopinava, ibuprofen, and two compound you design compounds. Yes. So then aspirin. So you may not do the aspirin. I already put the docking score for aspirin here. Aspirin is minus 4.8 kilocal. That's the unit for docking score per mole. Yeah, that's it. So I want you guys to give me the docking score for lopinava. Lopinava, don't forget, is our reference drug. Ibuprofen and two compounds that you designed yourself together with aspirin. Is it clear?
Yes.
Okay.
Yes.
Any questions? I don't want to. We're going to stop here today, but I know you have. If this is very straightforward, just take time, watch this video over and over, right? And you will get it. Let me stop recording.